Hi and a very good day. So in this video session, I will continue discuss one topic under box-Jenkins method, which is the assumption of box-Jenkins method. Alright. So actually, we already discussed the terms of stationery in our last topic. Alright. So the application of box-Jenkins method actually it describes the stationary time series. Okay, so that's why we have to determine first whether our time series is stationary or not. If not, then we need to perform some transformation first, okay, before we applying the box-Jenkins method toward our time series. And because of what? Because this box-Jenkins method it relies on the basis of stationary, where the stationary series, the meaning behind the stationary series is the statistical properties of series is actually the same even at any period of our observation period. Okay, right. So here unfortunately, okay, most economics data or are non-stationary. Okay, when we perform the first initial investigation of our series, we see that the data is not stationary. But the thing is, one of the particular characteristic of non-stationary data, it can become stationary. And by what? Okay, by performing what we call it as the differencing method. Okay, so here I will introduce what are the definition of differencing, the first differencing, the second differencing, to change the non-stationary series to stationary. Alright, okay. Here we can perform okay, test for non-stationary. Okay, we can determine whether our series is non-stationary or not by what? By simple observation of the plotted data. Okay, we can plot our original series, or also we will plot the ACF and the ACF plot to see whether it is stationary or not. I hope that you can differentiate between ACF for stationary and non-stationary, and also we can use statistical procedure to test whether our series is stationary or not, right? So for this statistical test procedure, I will introduce you what we call it as ADF test. Okay, based on the name itself, augmented DQ Fuller test. Alright. Okay, so here ADF test will test the hypothesis whether our series has a unit root or not. Okay, when it has a unit root, means that the series is not stationary. Okay, if our series does not have unit root, it means that the series is stationary. So we want for this hypothesis, for the stationary assumption to be whole, we need to accept, okay, we need to reject the null hypothesis to say that our series is stationary. Okay, so here you like I highlight in class, to make sure that you interpret the statistical test correctly, make sure that you know what are the null hypothesis and the alternative hypothesis for that particular test, and then what are actually the result that we want. So for this ADF test, we want to reject the null hypothesis. Okay, and the terms here we use integrated of order 0. Okay, what are the meaning behind integrated of order 0? I will explain in the next slide. Okay, so One of the properties of non-stationary series is it can become stationary by performing differencing. Okay, the differencing is actually we just the current series minus the past YT here is mean that the current series minus the past the last observation of the series. Okay, YT minus 1. So this is actually the differencing. Okay, so depending on how many differencings that we need to change the series from non-stationary to stationary, that's what we say the order of differencing. Okay, so the first order is we write the mathematical function like this. Okay, the equation is like this. We will use delta yt. So when you see this particular symbol delta yt, it is actually the differencing of that series. Okay, if you see this is the first order differencing. Alright, also known as if the series need differencing to become stationary at the first order, we also say that it is integrated or at order 1. Okay, if there is no differencing transformation that we need to change, it means that if our series is the original series itself is stationary, okay, we don't need to perform the differencing, so we say that it is integrated of order 0. Okay, so this is the example of this is how we write the first order differencing, and this is second order differencing. Second order means that even we perform the first order differencing, the series is still not stationary, so we need to difference it again. So that's why we need the second order differencing. Okay, so the mathematical function is like this. Alright, so be careful. Okay, so here we did the first difference of yt and the first difference of yt minus 1, and when we solve the equation, you will get this particular mathematical function. Okay, alright, so note that the order of the differencing is not the same as the different at lag. Okay, the pth lag. Alright, okay, so yang for this purpose, okay, I say that the second order differencing is different from the different at second lag. Okay, so when is actually we need this this particular at lag, different at lag, the lag. Okay, as example here for seasonal difference, and also for seasonal difference, where we have monthly data series and quarterly data series, and we need to perform the seasonal difference. The first order difference of monthly data series is actually yt minus 12, and for quarterly data series yt minus 4. Alright,